Hello again. This test stand is set up to demonstrate the effects of pulsation from a reciprocating pump with a high discharge and with a high inlet pressure coming into the pump. This simulates a tall tank feeding the inlet to the pump, and we've accomplished this by using a forklift with a tub of water approximately 12 feet in the air. The test stand consists of a 2-inch air-operated diaphragm pump, a Blaco discharge pulsation dampener with the adjustable control, a Blaco inlet stabilizer with the J model or inlet control. And we're using a transducer to be able to show you the effects of the pressure spikes created as the inlet valve balls to the pump alternately open and close. This creates a water hammer which can create a pressure spike that can damage the diaphragms in the pump, greatly reducing their life. The dampeners have been, as I said, overcharged, so their bladders have been pushed down into the inlet and they've shut off. So in effect, they might as well not be in the system. You can see the pulsation occurring at the discharge of the pump, and you'll observe that the discharge flow is pulsing and non-continuous up at the tub. As I dial in the pulsation dampener, you'll see the discharge pipe stop vibrating. You'll start to see a continuous flow at the discharge. And you'll see that the pressure gauge on the discharge is barely moving. We've now tuned in the discharge side of the pump. The inlet side is still shaking violently, and you'll notice on the transducer that the pressure spikes are reaching as high as 19 psi. Now, most air-operated diaphragm pumps tell you in their instructions not to exceed 15 psi with rubber diaphragms or 10 psi with Teflon diaphragms. So you can see that we can be doing damage to the diaphragms with this kind of pressure spike. As we tune in the inlet stabilizer, you can see in this specially prepared clear inlet stabilizer that the pulses, or the water hammer, is now being absorbed inside the inlet stabilizer instead of slamming into the pump. What occurs is that as this acceleration head from the high tank flows down and the inlet valve balls close on the pump, they stop the flow and the spike is created. The pressure spike can't go back up the discharge line because of the positive head. But the other side of the pump is opening its inlet valve ball to accept liquid. It's a low pressure area. The spike rushes over there, slams into the diaphragm and distorts it. With a rubber diaphragm, it stretches it, tends to separate it from its fabric, causing it to weaken and tear and fail. With a Teflon diaphragm, it starts to cold flow with this unbalanced pressure, stretches and fails. Now, if you notice, on the transducer, the pressure spike has been absorbed by the inlet stabilizer and is now averaging around 2 psi. That amount of pressure spike is well within the limit of the air diaphragm pump, and no damage will occur to its diaphragms. The valve balls will seat more positively. There's less chance of cavitation because we're accumulating liquid right at the inlet. Also observe that the inlet pipe is now vibration free and protected from damage to joints, threads, gaskets, gauges, and other components on the inlet side of the pump. We have, in effect, turned a reciprocating positive displacement pump into a centrifugal pump from a flow and pressure point of view. We hope that these demonstrations have shown that with the use of a discharge dampener on the discharge of the pump and an inlet stabilizer on the inlet side, we can protect the pump, the piping, and system components. We know that adding these components will extend the life of your liquid handling system components and, most importantly, protect your system, allowing you to transfer more product for a longer period of time between maintenance and repairs. Thank you very much for your attention.